I'm going to talk about a particular kind of particular kind of research that one can do um, with SOFIA about velocity resolved spectroscopy of shocks. And why are we interested in this kind of project? Well, one of them is about massive star feedback into the ISM. Massive stars stay close to their parent clouds. They live short, and they're not born with incredibly high velocities. So they tend not to go too far. And just in terms of basic numbers, the most for ISM and stellar feedback and star formation type research, some of the most interesting thing to memorize is 1 kilometer per second is a parsec per million years. So if uh, if the stars aren't more than uh, several million years old, and the clouds are of order a parsec in size, and the velocities are of order kilometers per second, everything should be hanging around together. Um, so while the stars are alive, radiation and stellar winds provide a substantial amount of feedback. And in fact, one of the SOFIA uh, primary scientific results was detection of the expanding shell around the Orion Nebula cluster, which we just saw images of during other talks today. Um, so we know that radiation stellar winds do it, and you can see the star and you can see the ionized gas, so you can pin the tail on the donkey quite well there. But at the end of their lives, and this applies both to O and B stars, or the more massive of the B stars, the stars abruptly inject 10 to the 51 ergs into their surroundings. And that's a lot more than the stellar winds. So energetically, even if stellar winds are doing a lot, there's a lot more coming, especially if you have a cluster with a lot of B stars in it, which make negligible uh, ionizing radiation in the big picture, but they still make 10 to the 51 ergs. Uh, and of course, the 10 to the 51 is a number that is empirical. And with new observatories like Rubin, we're going to see all kinds of different energies. We're starting to see a lot of bigger energies from the Zwicky Transient Facility and other experiments. But 10 to the 51 is a nominal number for a single supernova from a massive star or a white dwarf deflagration. So how big of a region is affected and what kind of densities? The useful number there is in the early phases of an expansion. If it's adiabatic, meaning no energy loss, then it's E equals mv squared. And if E is 10 to the 51 ergs, it's a number, and m is just density times r cubed, and v is derivative of radius with respect to time, then you can solve for that. The solution is that the radius goes as the 2/5 power of time, and you can solve for the radius as a function of time. And so again, in useful units, it's 19 parsecs for a 10 to the 51 erg explosion going into 1,000 particles per cubic centimeter gas if it's a million years old. So it's pretty big. It gets big very fast, bigger as the size of clouds. All right, so they're expected to overcome their birth clouds. Just examples of supernovae and their supernova remnants and their progenitors. Here's an example of one on the left where the explosion, well, it probably happened here near the middle, but now we can see the pulsar way over at the edge. And in fact, it's sort of cool. It's right at the shell, so you can even see where it's re-energizing the shell. This is in synchrotron radiation. And the famous Crab Nebula, often called a supernova remnant, but it's really a pulsar wind nebula, is looks like that. There's the progenitor right in the middle. We know it happens, and then there may have been hints of an infrared shell, but they're pretty tentative. So sometimes you can have a massive star become a supernova and not have much effect on the surroundings for a long time. So it actually was in a low density environment is what happened there. And then other times you see a beautiful supernova remnant like this one, SN1006, and there's nothing in there. There's no progenitor and no progenitor nearby, but that's because it's a type 1, and the type 1s are when a white dwarf completely explodes and they don't leave anything behind. Anyway, I'd love to look at these things. So in terms of looking at a somewhat bigger scale, this is one of the most influential papers in star formation is the Elman Green and Latta paper. in 1977 in their schematic, they show an OB star association. Uh, it has an H2 region around it. And in this case, they drew the OB association outside of their molecular cloud. Just take that as an example. It should probably be inside often. But if they happen out to the side, it's easy to see that you have an H2 region. And then in a molecular cloud, you have this compressed layer. And in the compressed layer, they speculated that stars would form, and then this would happen again. Then these stars would become these stars, essentially, and drive another layer. So that's the famous sequential star formation idea. There's a lot of circumstantial claims about it, and I would say it's a great idea, and it gives a lot of basics. But what we want to do is address this observationally, because theoretically it's an unbelievably messy and intractable problem with all the complications about the actual natures and the stars. So let's see, and then now about dynamics and time scale. So I talked a little bit about time scales related to the explosion, but in terms of the relation to, we need to keep track of all the time scales, because if you don't, then on the theory side, you can get instantly confused. For one thing, a given piece of ISM tends to get hit by, go through a spiral density wave of order once every 100 million years. Free fall time for gravitational collapse, this is an important one for this project, is of order million year if the gas was 10 to the 3 particles per cubic centimeter. Cloud crossing time, I already told you the famous convenient units is, it comes out to 1 if you put the radius velocity in the normal units. The time scale for CO formation, so this is from a chemical evolution model. Time scale for CO formation, also about 1 million years. So a lot of times you can have molecular gas without CO because of that. And then the cooling time is much, the KTO times the cooling rate. That's much less than 1 million years. So cooling is almost instantaneous, but chemistry isn't. And dynamics are similar to cloud and star formation times. That's what you get out of this. Okay, and just for fun, a simulation of the simulations of the ISM do show very complicated structures, and because the speeds do cross the sound speed, there are in this case it was a turbulence over the thermal sound speed was 10, so it's Mach 10. So this is all these are shocks, strictly speaking, even though sometimes it's called turbulence. It's supersonic turbulence. All right, so then, so the way to quantify the amount of influence that an explosion is going to have on the surrounding cloud is using the Ram pressure. So the Ram pressure, convenient units. Convenient units are here. We just do it as NV squared. That's actually P over K, the Boltzmann constant. All right, so just call those pressure units. So for the supernova remnant IC443 and those units, the pressure, which depends on the age of the supernova remnant and the pre-shock density, is 300,000. And it was shown in a paper by Roger Chevalier that the pressure gets 10 times higher in dense clumps, because the interclump medium shocks also push in on the dense cloud. In the diffuse ISM, pressures are observed to be like 20,000, so a lot less. But just for reference, the thermal pressure is only estimated to be about 2,000 in those units from UV lines. So the diffuse ISM itself is already stirred up and probably shocked. And then in the supernova remnants, it takes it up yet another notch. I just want to mention that in PDRs, a lot of time people talk about PDRs and only as photo dissociation being the only thing going on, but then derive in these same units pressures of order 10 to the 8, so 100 million. Wow, that's a high pressure. So there's that doesn't happen without needing also to understand dynamics, the same way that we're going to do for the supernova remnants here. It's certainly not a static region, so static PDR is sort of a misnomer. Let's see. All right, so here's an example of a supernova remnant that we're going to investigate in this talk. It's IC443. It has, this is a WISE image, multicolor. And the part down here with the distinctive blue colors, these are just wideband images, but those colors are interpreted as molecular hydrogen emission. It's also a very similar result you get with 2-mass, so it's very bright. You can even see it in 2-mass. And what we were trying to do is look at the densest clumps, and these are very well known. Many papers have been written about these because they're very bright and interesting. And the angle that we're after in this work is can they be sites of star formation, and what's the nature of the shock fronts into the most dense gas? Xes is very good for this. The slit length is about right, the velocity resolution is about right, and then if you compare it to the size of a pre-stellar core, if it were shocked, then those units also come out about right. So for a core of order solar mass and of a molecular cloud with of order 10 to the 3 particles per cubic centimeter, its size would be this, and that fits nicely into the Xe slit. Or it's a little bigger, but the point is it's not infinitely bigger or smaller. So Curtis mentioned the modes of Xes. Here's an example of the medium resolution mode. It's not as much used, but this one we did pretty much as a finder. The great thing about this medium resolution mode is even though its resolution it wasn't really good enough for this project. We did it to look at the shock fronts and make sure we're pointed at the right place. So the great thing is very easy to analyze. It's just a long slit spectrum, very easy to understand, has a very wide velocity coverage and a long slit. So you can see spatially, you can see structure along the slit. The disadvantage is the telluric features will easily mess up your line, like in this case. Resolution, we weren't very confident about this line, but eventually we were, after looking at it for a long time and making these very careful reductions. But you can have blending between telluric absorption, which is shown in blue, and the emission, which is shown in black. But this one did turn out to be interesting. You could even see a velocity shift in the medium resolution. So I'll come back to that in the interpretation part. With the high resolution mode on Xes, technically the high medium mode that Curtis explained earlier, you get very good velocity resolution. So you can see now it's not just, everything doesn't just look like Gaussian. Now you can see these cool shapes. And obviously you can see the shifts. You can see that the pre-shock gas in this case is at about 3 kilometers per second, as I recall. So it's around here. So you can see not only line profiles that are interesting in width, but also in shift. And both of those are very important for interpreting the shock. And also the telluric feature is very clearly separated. And that depends on time of year. I don't think we mentioned that, but there are ways to move the telluric features around relative to your source, depending on exactly when you observe scheduling. All right, and just to show some non-SOFIA data, because other telescopes exist also, here's from SWAS, submillimeter wave astronomical satellite, a spectrum of one of these IC443 clumps, and you can see this very broad line of water, also carbon and high JCO and also low JCO. But you can see these lines, they're certainly not a Gaussian or multi-component Gaussian. It's symptomatic of a smooth change of temperature as a function of something. And I'll show you what it is in a sec. So to interpret these shocks, let me just watch the clock and see how I'm doing. We use the Paris-Durham shock model. This link is in the resources that Ariel posted on the school website. It's a very advanced and accessible model. It has very detailed chemistry in it. So that has tremendous advantages for understanding molecules other than the main ones like hydrogen, even though that's what I'm going to work on. It does include the magnetic field. It is an MHD shock. Just truth in advertising, it is very limited in the following ways. It's only one-dimensional. And obviously, you saw the cool ISM simulation pictures. Obviously, there's multi-dimensional effects going on in shocks. They're inherently not 1D when faced with a symmetric surrounding medium. They can't treat fast shocks. It just doesn't work. It doesn't give the right answer because they neglect, it neglects radiation from the shock itself, like the ultraviolet uh, and visible light that you get when you ionize. So it doesn't do that part right. So there are limits. It's perfect for this exact project, but it doesn't smoothly go to the faster shocks. So when if you do install that model and run it, to compare it to your data and to understand what's going on, like a lot of the codes these days, the output files are written out in a slew of ASCII text files, ASCII tables. And the great thing about that is you can read them in with whatever. We use Python, as you can recognize the Python color table in our plots. But you can read those in with whatever and post-process to figure out what you want to see. So we wanted to see the emissivity of the line we proposed to observe, which is the S5 line of pure rotational line of molecular hydrogen, as a function of distance behind the shock for a number of different shocks. And for the very broad profiles, the interpretation is going to be that we probably saw gas with a lot of with indication of dynamic shift. So not just a wide Gaussian, which could just be warm gas, but these triangular profiles like I was showing before. That's temperature varying as a function of distance behind the shock is probably what's happening. So you're probably not seeing a shock like this one here, which is just a spike. It's actually very close. This one is also cold, although this axis doesn't show it. So that should give a narrow line pretty much centered where the pre-shock gas was. It should be more like these others that are spread out. So you see emission from a wide range of distances and temperatures, but more importantly, the velocity shifts as a function of distance behind the shock. Okay, so and I guess the point I was trying to make there is even with a shock front, it's not like it's right, it stays at one velocity. There's the emission from all the gas at intermediate velocities, and some of them aren't sped up by much, and some of them are sped up by a lot. These are now the velocity profiles. So this is an observable spectrum. Same shocks as from the previous figure. The red one was a very dense cloud, and basically it's like it says if you go to a very high density, it's like the shock hits a wall and it doesn't move. So it stays at the pre-shock velocity and gets heated up, gets excited. That's nice, but it stays at this velocity. Whereas a lower density medium, like this blue curve, it gets moved. So that's why the center is off. And that's something that's often neglected. And it took my excellent coworker, Trom, and I many discussions to get this right. We can interpret the shift. That's actually a key part of interpreting this. All right. And then we can make fits and try and use the models to explain the line profiles. And you can see, well, top one looks great, this one looks great. We can explain the tails, and that's due to, as I was saying, the velocity shift behind the shock due to acceleration. But sometimes the tails are too big. We can't do it, and that could be because there's even faster shocks that the Peristurm model can't do. And that's how we interpret this. So we interpret most of the line profile using a shock that we can model, and then the rest, like in this one, there's almost no emission at the rest velocity of the molecular cloud. It's all at this high velocity. So that's probably some lower density stuff that has been shot away like a bullet by the shock front. Not really like a bullet, swept up by the shock front is a better way to put it. And then this is the intermediate case where you have both. Okay. Oh yeah, little circles to show what I was pointing at. Okay, so another aspect of this, so I was really into the velocity part because the high resolution spectroscopy is what we can do there, but also if you look at the intensity of lines at different excitation, and we did see this in previous talks, like Archana's, exactly this kind of thing. If you look at the excitation as a function of the energy above ground state of the upper level, then you can see that, well, it's not a straight line. It should be a straight line if it's in local thermodynamic equilibrium. So obviously it's not an equilibrium piece of gas. And also you can see what the predictions are of our shock model. So if you take the model that fits the velocity profile for this line, well, then you get this set of points here. So in fact, the shock cannot explain this. The shock that explains the S5 line can't explain these other lines, S0, S1, and S2. So this is work that that Trum is doing right now, and so it's combining excitation diagram plus velocity profile. Oh yeah, and so we actually, that's also subject of our current proposal. Hope it does well, and I hope yours do too. We observed the S5 line already. Now we're going to try and observe the velocity profile of the S1 line, which should have a distinct profile, a narrower one, and then we'll use the dynamics to fit a shock to that, and hopefully it holds together. But we don't know. It's an observational project, and the reason that's so important is that that would be the colder gas, slower shock, meaning higher density, and that's the gas with the shorter free fall time and most likely to have star formation. So that's why that's actually extremely interesting. All right. H2 isn't the only interesting line to observe. There's also high JCO lines. Well, here's the regular CO2 to 1 ground-based millimeter wave line, 1 millimeter actually line, and here's a high J line done with SOFIA. We use the same exact techniques of post-processing, but in this case, there was the challenge that CO becomes optically thick very easily. And so there's a student working with us, Fuda, has written a paper about that, trying to include a radiative transfer as post-processing of peristrum shock model for CO lines. And then a shout out to David Neufeld. I don't know if you're still on, David, but in his paper, and he mentioned this, I think, in a question, but if you look at the velocity profile, this is for a Herbig-Haro object, so it's also shock, but it's triggered by a jet, in this case, a stellar jet from a young stellar object. You can see that the velocity changes for different lines, and it changes in this odd-even pattern. And that is because not the gas, well, we already said there's a temperature gradient behind the shock. And not only does that change the excitation, it also changes ortho to para, so it can actually change quite fast. And so you can see it's an independent measure, which you can get actually just from the velocity, which has great advantages of not, and depending on the intensity scale, you can get temperature versus distance behind the shock diagnostic just from the velocities. And if I haven't done a good job of that, you can help me out and correct me, David. All right, and the last thing I wanted to share is just a list of here's various projects from the SOFIA archive, some published, some not very published, that one might consider taking a look at, which could have data relevant to this kind of research. And that's it.